Welcome back to Honors Calculus. In this video, we're looking at the second derivative test. The second derivative test is going to allow us to extend the idea of concavity that we were talking about previously. In order to understand what I mean, let me get my head out of the way and let's start drawing some pictures. We know that a function can be concave up or concave down while it's increasing or decreasing. All right, so a function that is concave up and increasing is going to be a curve that looks kind of like that. A function that is concave down and increasing is going to be a curve that looks something like that. Exponential and logarithmic is kind of the way I think about those. A function that is concave up and decreasing is going to be the mirror, and likewise concave down and decreasing will be the mirror there. So we have these shapes in each of the four possibilities: concave up, concave down, increasing, or decreasing. A maximum we know occurs when increasing turns to decreasing. I drew that picture using lines previously, but we can also think about that as curves. So we want to go from increasing to decreasing. And we can do that when we are concave up increasing and also concave up decreasing. We can do that when we are concave up increasing and then concave down decreasing. We can be concave down increasing and then concave up increasing. And we can be concave down increasing and concave down decreasing. In the first three of these pictures, that maximum is going to occur at a cusp. A cusp is a place where the derivatives are undefined. Or sometimes y prime itself is undefined. But this place here, where the function is smooth at that maximum, we in fact have that the function is concave down at its maximum as well. And we can do the same thing with a minimum. I'm not going to go through and draw the pictures, but you'll see the same situation come up again. All right. So for a theorem, let's let f be a differentiable function, a function that's differentiable everywhere, and let's let c be a critical value. if f double prime of c is less than 0, then f of c is a relative maximum. And if f double prime of c is greater than 0, then f of c is a relative minimum. When I was first learning this, those inequality symbols always threw me off. If f double prime is negative, then you have a relative maximum. And if f double prime is positive, then you have a relative minimum. If your instinct is like mine, you're backwards on that at first glance. So take a moment and look at that and make sure that you remember which one is which. But understanding it, making sense of it, makes a lot more sense when you think about it in terms of the graph. If f double prime of c is less than 0, then that means that the function is concave down. A function that is concave down looks like this and has a minimum, never a maximum. I'm sorry. If it's concave down, it looks like this. It has a maximum and never a minimum. And if f double prime of c is greater than 0, then that means that the graph looks like this. And that tangent point can be a minimum and never a maximum. Again, that set of pictures that I looked at going into this at the beginning. In order for it to be concave up and be a maximum, you have to have a cusp. And when you have a cusp, the derivative is undefined. And so, in fact, at that point where the cusp occurs, you don't have concave up. You have concave up everywhere around it, but not at the point itself. And so our ideas of extrema and our ideas of concavity really work well together. If you are checking a function and you are looking to find out where the extrema occurs, and you are also checking to see where it is concave up and concave down, you can save yourself a step and recognize that you only have to check once. If it is concave up, then the extrema are minimums, not maximums. If it is concave down, the extrema are maximums, not minimums, and you don't have to test otherwise in order to determine which thing you have. If you're not already going to the bother or planning to go to the bother of testing the concavity, it's not all that useful. But when you are planning to test concavity, it really helps you out. And when you don't have a lot of information about the function, you know the derivatives at a single point, you don't know what the derivatives look like elsewhere, then this can be your method of last resort. So there are a couple of places where situationally this is really useful. In general, it works, it exists. For the rest of this lesson, we're going to be looking very specifically at the applications where it exists, and we'll extend that in on to a future lesson tying everything together. All right, let me get my head back out of the way and let's actually close this proof. I know it's not a great proof. Most of the proof is that introduction that I gave you. But thinking about the visuals of why this is happening makes a lot more sense in understanding why it's happening than anything else. And now that we know that it is a thing that happens, let's think about the function f of x equals x cubed plus 5x squared minus 9x plus 7. And I'm asking to classify any relative extrema. You can do this with just the first derivative and testing intervals. It absolutely works. We've done it before. There's nothing that changed there that prevents it. But I want to test, or I want to show how this new process of the second derivative test works to do the same thing. So the first thing we're going to do is look for some critical values. We will find critical values by differentiating. The derivative here, f prime of x, is 3x squared plus 10x minus 9. We'll go ahead and set that equal to 0 and see what comes out of it. In this case, not a whole lot, right? 3 times negative 9 is negative 27. I need two numbers that multiply to negative 27 and add to 10. I can't think of anything. So I guess I'm going to go straight to the quadratic formula. X is the opposite of b, that's negative 10 plus or minus the square root of b squared. 10 squared is 100, minus 4 times a times c. 4 times 3 is 12. 12 times negative 9 is negative 108. So minus negative 108 is plus 108, all over 2 times a, which is 3. 2 times 3 is 6. All right, so 10 plus or minus square root of 208 over 6. See, 208, I can see that it's going to be divisible by 4. Let me grab my calculator real quick. 208 divided by 4 is 52, which is actually also divisible by 4. So I can factor 208 as 13 times 16, which is nice because the square root of 16 is 4. All right, so simplifying that a little bit, I get that my critical values occur when x is negative 5 plus or minus 2 square roots of 13 all over 3. Right, that's something that I can do by hand. I used a calculator because I'm lazy, but I could have gone off to the side. I could have set up my prime factorization tree and just kept dividing by 2 until I realized that there were 4 factors of 2 in there. 13 is a prime number, so I know at that point I'm done. All right. Now, if I was going to keep using my calculator, I'd be very happy to just keep going through, punch this into my calculator, get a decimal approximation, and I could use that from there, right? Square root of 13 is somewhere between square root of 9 and square root of 16. So somewhere between 3 and 4. So we're looking at, let's see, negative 5 minus 3, or minus 2 times 3 is negative 11. Negative 5 minus 2 times 4 is negative 13. So somewhere in the general vicinity of negative 4. And then the positive one will be somewhere in the vicinity of 1 or 2. And you can test around there if you're very careful to avoid the points in problem. Or we can just go back to the derivative that we've already taken. Let me copy that so that I can keep using it. Paste it over here. And we can test concavity by taking the second derivative. F double prime of x is going to be 6x plus 10. Plug these values in, because again, the only thing we care about is what is happening at these points. So we have 6 times negative 5 plus 2 square roots of 13 all over 3 plus 10. And we get negative 10 plus 4 square root of 13 plus 10 which is 4 root 13. And the only thing that really matters is that that is positive. And then we plug in 6 times negative 5 minus 2 square root of 13 all over 3. We get negative 4 root 13, which again, the only thing that matters there is that it is negative. When the second derivative is positive, that means that the function is concave up. And when the function is concave up, it is possible to have a maximum, not a minimum. When the second derivative is negative, that means that the function is concave down. And when the function is concave down, it is possible to have a minimum, not a maximum. So we can classify right there. We have a maximum, we have a minimum at these two respective points, and that's all we need here. All right, here's one I would like you to try. I would like you to use the second derivative test to classify all of the relative extrema for the function g of x equals x to the fifth minus 5x cubed. All right, take a couple of minutes, see what you can do with that problem, and I'll see you in the next video.